Alright, so today we're going to talk about transformations of exponential functions. Before we do that, I want to ask you guys some questions. I'm going to come over here onto the side of this paper. Okay, we're not going to use any of this paper over here. If I said to you, what is the parent function of a quadratic? What would you tell me? Y equals x squared, right? What's the parent function of a square root function? Y equals the square root of x, right? What's the square root of a cubic? Y equals x cubed. What about a cube root? Yeah, y equals cube root of x. What about absolute value? Y equals absolute value of x. What about rational? Y equals 1 over x. What about linear? Y equals x. These are all parent functions you're familiar with, aren't they? Aren't you? These are all, doesn't matter. You're familiar with all these, yes? Because we've already studied them, right? So when we got from quadratic to square root, or from square root to cube, or cube to cube root, you knew what the patterns were for transformations, right? Now, that doesn't really change here when we talk about exponential functions. What does change is this. While there is one parent function for absolute value, while there's one parent function for quadratic, there's one parent function for square root, there's not that for exponential. Because it could be y equals 2 to the x power. Right? What other numbers is 2 allowed to be, but still keep it an exponential function? Like any number, right? 3, 7, 12, 10, a half, 3 halves, anything like that, right? So you kind of got to use what you're given. We can't just go back to one exact function because it really depends on what you start with here. Does that make sense? Before, everything that changed was up in the exponent. Now, because it's called an exponential function, that's where our variable has to be. So our base is allowed to change, and we need to be okay with that. But the good news is that it's okay, right? It doesn't have to, we don't have to worry about that 2. That's just, the 2 is what gives it the shape. Like the steepness or shallowness or growth or decay, something we're going to be talking about in the next couple days. Okay? So if I say, here's this function, and here's this function, can you tell me how this one is different than my original function? How do you know that? How do you know that it shifted up 4? It's adding 4, right? That's what you said. Well, how do I know that that's not moving left 4? Yeah, so what we've talked about with all these other parent functions are, we've actually used the words inside and outside, haven't we? It's either inside or outside of the parentheses or the absolute value sign, or inside or outside of the fraction, inside or outside of the root sign. What are we talking about when we talk about exponential functions? Inside and outside of what? The exponent. That's exactly right. This is outside the exponent. It's not part of the exponent. So that's going to follow all of our outside rules. It's going to be a vertical change. Okay? What if we had y equals 10 to the x power, and then I said y equals 2 times 10 to the x minus 1? How does this one change from the original function? So we know it's going to be a horizontal shift. Why do you think it's, wait, is it left or right?
It's left.
Wait, right.
It's right, because remember, if it's inside, it's going to be opposite of what we think, right? Minus makes us think it's going to move left, but we know it's opposite of that, so it's going to move right. So we know horizontal shift, right, 1. What else happens? The horizontal shift right one happens because of that. What else is here that's different from the first one? The 2. Now I hear you saying vertical something or other. That's right. Why is it a vertical something or other? Yeah, it's outside, right? So a vertical what? Well, that's a good statement to make. It's a question, a conversation we need to have. Can't remember if it's a stretch or compression. What makes it a stretch? What makes it a vertical stretch? What makes it a vertical compression? Close. If it's a number,
if it's less than 1, or if it's
so if it's a number greater than 1, it is a stretch. So this is a stretch by a factor of 2. What makes it a compression? Less than 1 and greater than 0, right? In between 0 and 1 will make it a compression, a vertical compression. Okay? So now I'm going to try to trick you. But I'm warning you of that fact up front. So don't let yourself be tricked. Okay? Y equals 2/3 to the x power is our original exponential function. And we're going to say y equals 2/3 to the 3x power. And we'll throw in a plus 2, just for fun.
okay, it's vertical or horizontal compression by a factor of 3.
Okay, so here's what he said. Horizontal compression by a factor of 3. I thought we just said if it was greater than 1, it's a stretch.
It's an exponent, so it's backwards.
Since it's inside, it's opposite of what we would think. Remember us? We just had that conversation about this, the -1. If it's inside, opposite what we think. Here, it's the same thing here, guys. We think this is probably a stretch because we know if it's greater than 1, it's a stretch. But since it's inside, it is a compression. Okay? What else does this one have that we wrote in just for fun?
Stretch.
Vertical
Shift, not
shift
sorry, all this shift is in my mind.
of 2. Okay? Now, there's one more thing that you're going to see in your textbook today when you go through these problems, and I don't want you to freak out when you see it. I want to make sure that you're okay with it. And it's going to be this. Y equals e to the x power. I know that for your entire life, starting with your parents, your kindergarten teachers, your elementary school teachers, even your high school teachers have told you that E is a letter. Well, that's because it's true. But when we get to high school math, especially Algebra 2, we have to talk about the number E. Okay? Founded, discovered, I don't know what the right word is to say, by a man named Leonard Euler. Leonard Euler. You see why we use an E?
Yep.
Because his last name starts with an E. Okay? This is the number that he discovered, developed. I don't know the right word for that. Okay? Or maybe it was just attributed to him. I'm actually not quite sure. That's something that you could look up.
Maybe the E was for the second to the last of the
It could be this E. You are correct. It could be this E.
Or it could be the E in the second L. You know.
All that being said, this is a number. Do you want me to show you where it comes from? All right. Don't be afraid. All right. Don't be afraid. This sign right here is a summation notation. It means we're going to add up a whole bunch of numbers. We're going to use this formula and start at 0 and go all the way to infinity, adding up these numbers. So is this like a real number? Is this a rational number, I mean?
No.
Can we write it as a fraction? No, because it's a bunch of numbers added up and we go all the way to infinity. I mean, I haven't gone all the way to infinity because it's impossible. Right? Kind of like pi in that sense, right? Keeps going and going and going. It's an irrational number. It can't be written as a fraction. It comes from fractions, okay? This says we're going to start at 0 and go all the way to infinity of this. Now, this does not say 1 over n. That's not what it says. It's 1 over n factorial. And a factorial, well, this is how it starts out. 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, 1 over 3 factorial, and on and on and on, right? Well, 0 factorial you just have to know is 1, so that's a 1, right? 1 factorial I want you to know is 1, and I'll show you what it means here in just a second. 2 factorial means 2 times 1. So that would be 1 over 2. 3 factorial is 3 times 2 times 1. So 1 over 6, right? What is 5 factorial? 5 times 4 times 3 times 2 times 1. Okay? Factorial is used a lot in probability. All right? Just so you know about that. All right?
This is in college algebra.
This is in college. This is something, yes, you would talk about in college. Okay? But that's where this number e comes from. It's stored in your calculator, obviously up to a point, because your calculator can't store a non-ending number, right? It just stores it up to a point. But this number e is going to show up in your homework tonight, and I want you to realize it is a number. It is a constant. It has a value. This e is not a variable. It's not something that changes. Okay? So if I say, here's my original function. Tell me the equation of something using this base that goes up 4 and right 2. What's that going to look like? Up 4 and right 2. Well, we're going to have e raised to what power?
X.
Yes.
2.
Perfect. X minus 2.
Plus 4.
So, but a big plus 4, right?
Yes, ma'am.
So I use this base just as I would use this base, just as I would use this base or this base. It's not anything different. It's just, well, I mean, it's kind of different because it looks like a letter. Fair enough? Any questions about this? Now, you're right. I'm not giving you a whole lot of examples. Why? Because we've already done it, right? How many times have we already done it? 1, 2, 3, 4, 5, 6, 7 times this year we've already done transformations.
That's my favorite thing to do.
Okay? Transformations you guys are getting really comfortable with now. I wanted to give you something, though, that you have a very firm basis in when we start exponentials, something that you really understand and can be confident about. Okay? Any questions?